So recently as a group, we went fishing and we wanted to discuss how to maximize the cast of the lure. We thought, what better way to do it as our dynamics project? We want to keep all our variables standard, so standard reel, standard rod, standard line, standard cast, but we wanted to change the setup of the line. Our goal was to analyze the dynamics involved in the casting by changing the weight placement, and in this we changed the weights in two different places. We had the weight right next to the lure and the weight 6 inches above the lure. Our attempt was to use this knowledge to discover how it would affect the flight of the lure and which one would maximize the distance of the cast.
We began our experimentation process by first selecting a suitable location to cast the lure. We decided to use the top of a parking deck where we had a solid backdrop for videoing each cast. Once we had selected an open spot to cast, we set up our fishing pole by first placing a weight directly against the lure, which was located on the end of the line. We then had one person cast this setup 3 times in order to keep the casting motion and release point constant. Each time we attempted to release the lure at an angle of 90 degrees, which proved to be quite difficult. Most of our casts ended up with an angle between 45 to 90 degrees. Next, we moved our weight a distance of 6 inches from the lure and repeated the previous steps, measuring the total distance that the lure had traveled each time. With a total of 3 casts completed for each setup, we could begin our calculations. We began by calculating average angular velocity of the lure for each setup by using omega equals d theta over dt, where angle was measured by placing an angle finder on the computer screen while the video was paused at the exact moment the lure was released. The time was measured by using the number of frames per second for an iPhone and counting the number of frames from start to release. Next, we calculated the initial velocity by using v equals omega cross r and split this into vx and vy components using a right triangle. At this point, we were able to use basic kinematic formulas to calculate the values for time of flight and total distance traveled using data from the film. We repeated the same process for the 6-inch setup, with the only difference being that we had to take into account the fact that there were 2 angular velocities acting on the lure. Through the use of the equation v equals vb plus omega 1 cross r1 plus v relative, we were able to find the velocity of the lure. Using this equation, we determined that v was the initial velocity of the line upon release, and vb was the velocity of the origin, which is 0. The relative velocity is then the velocity of the weight compared to the velocity of the rod. This gives us our final equation, v equals omega 1 cross r1 plus omega 2 cross r2.
Okay, so I'm going to take you through the math of our project. This first set is from cast set number 1, and it's with the weight and the lure as a point particle. This is a diagram of our projectile motion. So we have the radius of the rod, r, and it travels through an angle theta with an initial angular velocity, omega 1. It has an initial velocity, v naught, travels a total vertical distance, delta y, and a total x distance, x. And from our videos, we had data from our 3 casts, and so we measured a d theta, a dt, and a total x from those videos. And from d theta over dt, we calculated an omega for each of the casts, and just took the average to get the omega we used to calculate v naught. And since r is the same for each cast, we just used omega average instead of v naught average. And from there, we just did very basic kinematics of finding the x and the y components of the initial velocity. And in the y direction, I went through and found the total delta y, so the total vertical distance the lure travels, and found the total time that it was in the air. And from there, we found the total x displacement that with that initial velocity, it should have gone. For cast set number 2, this one is with the weight 6 inches below the lure. So the setup is a little bit different. We have our same R1, but we also have the second radius. And so as R1 travels through theta, R2 also travels through phi, which gives us a second angular velocity that's applied to the lure. So again, through the videos, we measured d theta and dt the exact same way, and we also found a total x displacement. And then for R2, we had a different d theta and also the same dt. And the equation we used for initial velocity here was velocity of the weight with relation to the origin, and also velocity relative, which is the lure with relation to the weight. And so from these 3 casts, we found an omega 1 and omega 2 for each. From that, crossing with R1 and R2, we found a V naught for each. From there, I just went ahead and took a V naught average at 57.71 degrees, which is the average of our d thetas, And use that as our initial velocity. And from there, we did the same exact kinematics to find the total delta y, so the total vertical distance, the total time that the lure was in the air, and the total distance that the lure should have traveled with this initial velocity.
Okay, so after we were done with our calculations and our experiments, we could then analyze our data and draw conclusions from that. Looking at cast type 1 with the weight placement at the lure and looking at it as a point particle, looking at our experimental values, we were able to see that we came up with an average of about 20 meters for each cast for our distance. And our calculated values ended up being around 14.78 meters. For cast type number 2, which was the weight 6 inches below the lure, we had an average of about 18 meters. And our calculated value ended up being around 18 meters as well. So these ended up being fairly similar. We determined that the cast type number 1 with the lure, the weight on the lure, it would be significantly shorter than if the weight was 6 inches below the lure, approximately 19% more than if the weight was at the lure. This difference in our values can be attributed to a number of reasons, one of which being that the wind resistance from the top of the parking deck where we conducted our experiment caused the lure to track off course and not go its projected distance that it could go. Another could be that as I was trying to cast it, we were trying to get a release angle of about 45 degrees, but it was difficult to recreate that each time, and also to keep the same velocity of the cast each time. So that could have attributed to these differences in values and these differences in values as well. Also, the line could have gotten hung up on the spool for a split second, and that could have caused it to come up shorter than it should have gone. Theoretically, in a perfect environment where, an indoor environment where all our stressors, there are no stressors, and everything is constant, we could come up with these numbers, but doing it in the real world and doing it just when you're fishing, you can come up with something like we got here.